Right. So yeah, I'm talking today about API horror stories from an unnamed co-working company for legal purposes. Yes, it's that company. Um, and I was basically kind of asked to go and work at that company because they have terrible APIs, in their words. They were like, everything's terrible. Please, can you come and help us? So I did. And there were so many problems. We don't have time to get into all of them, but API A would talk to B, C, D, E, all synchronously and entirely in web threads, which is a recipe for disaster. Um, some of those APIs individually could take 2 to 5 seconds on a good day. And that means on a bad day, it was more like 20 to 30 seconds for some of those APIs. So things were pretty slow. What made it worse was that the APIs were designed so badly that they were both suffering from overfetching and underfetching at the same time. You'd have to hit lots and lots and lots of different services and different endpoints to get your information. But you'd also get more information shoved into that response than you really wanted, some of which was being calculated on the fly, and so were very slow, and you didn't even want it in the first place. There was no HTTP caching anywhere. No one used it at all for anything. So those poorly targeted, very slow, badly designed endpoints were always the slowest they could possibly be. You could never reuse a response, even when the data was very much the same. Different error formats would be emitted from the same API, different versions, or sometimes different endpoints would have their own unique Snowflake custom error format. And so people would try and write generic code that would say, oh, if we get an error, use this. And because it was JavaScript, the customer would end up seeing error, object, which is ridiculous. Auth was enabled on a per endpoint basis in this Ruby code. And if you didn't enable auth for an endpoint, it just didn't have any. But because all authentication was disabled in testing, the testing was just unit tests. It meant that they'd kind of skip the tests in the unit tests. And so quite often, really sensitive data would be just omitted in production because there was no authentication on any of it. So there were a lot of scary things. But the worst part when trying to figure out, like, okay, I'm coming in, I'm trying to help fix all this stuff. What are we gonna do? First question was, so where's your API documentation? And there wasn't any, none anywhere at all. So after trying to figure out why, a lot of the time they were like, we don't have time to write and maintain documentation. We just, rewrite it if we forget how it works. And this is like a genuine thing that people would do. They would legitimately just rewrite the API if they forgot how it worked. It's kind of the foundation for me learning about the API design first workflow, and several years ago trying to refine it and improve it and build tooling around it, because they would do it very much the worst code first way possible. They would decide that they had to make an API somehow. They would, plan it on a whiteboard or in a meeting or in notes or on a napkin, whatever. They then, share that napkin around between the API developers, who would spend a lot of time writing a bunch of code, and then they maybe give it to the customer for feedback. But because they spent so much time writing all that code, it was pretty much close to the deadline, and they couldn't necessarily get all of the feedback done. So they'd end up deploying the close enough API and having a big celebration, saying, we did it, yay, let's go to the pub. And maybe we'll write the API documentation later. But first we should probably, a few of us want holidays. A few of us need to work on this feature. A few people need to work on bugs or performance issues. We'll do 1.1 and 1.2, and we'll get there later. And while they've been doing all of that, a new customer's appeared, maybe 6 months later. They have no idea how the API works because the documentation doesn't exist or is bad sometimes if it exists. This company, it didn't. And the API developers in that time have legitimately forgotten how that exactly works. They might not remember exactly what the different statuses mean or which combination of Booleans has which effect, right? So they try looking at the code, and because of a few rewrites trying to hack performance, it would be too confusing. So they just make a new API or a new version, and you end up with multiple global versions of an API that are literally just for different iPhone, web, etc. So no client would be able to use the newer versions of the API because, firstly, it was designed for another client's requirements, right? It wouldn't necessarily work the way they wanted to, or it wouldn't be able to solve the problem they wanted it to solve. So no clients would be able to use other versions, which meant they were stuck maintaining version 1, 2, 3, 4, 12 forever until one of those clients vanished or got rid of their app. And even if the clients were able to, use that theoretically, there was no documentation, so they'd never be able to figure out how to actually do it. So the solution here, I went to work at a company called Stoplight. We make a bunch of tools that solve all these problems, right? It's nice to be the customer we're designing solutions for because I feel all these pains. We came up with we support the API design first workflow, where you design a bunch of open API. You can write it by hand or use a GUI like we make. You can then give mocks and docs to your potential customers, multiple potential customers, hopefully. And you can get customer feedback on those mocks and docs. They can interact with like a fake API to see how it works when you haven't written any code. And it means that you can just tweak a little bit of YAML and make the APIs. And you can keep saying, is this what you want? Is this what you want? Does this work better? Until you've got something, and you can iterate on that really quickly because you're not rewriting all of the code every time you try and iterate. And then once the customer's like, yeah, this is great, you've got your open API living in your GitHub repo. You can use that open API to simplify the code that you're about to write. You can use it for request validation. So requests coming in with a generic middleware, it can say, oh, that email should be this format, or that string's required and you haven't done it. It can take care of all that stuff that you normally have to write, making your requests really easy. And then you can use it for your contract testing and your responses. So you don't have to spend loads of time in both places saying, yes, this is an email. Yes, this is required. Yes, this is a string. Yeah, you used to do that in several places. Now you just do it in OpenAPI, the source of truth. And it means that when you deploy your code and your docs are completely up to date because they use the same source of truth. Tests are up to date too. Everything's the same. And what that means is that when new functionality is requested, or when a new customer comes along and they need something slightly different, you've already got that open API completely up to date and completely accurate. So there's no more like, whoops, we forgot how this works. We'll have to try and figure it out. So if you want to give that a try, free account on Stoplight.io, you can do lots on the free account. I'm not here to sell anything. It's pretty cool for free. The next thing is something I call Cache Stampede Cluedo. Cluedo's the game where you have to figure out who done the murder in the library with the candlestick, right? That was what we had, but with a Cache Stampede. Cache Stampede, if you don't know the phrase, is when you have an application that is kind of reliant for its performance on a cache being there. Like every request that comes through hits this cache when normally it would hit some other third party or some other API, some dependency. And the only reason it's really working is because your cache is there holding back all that traffic from being unleashed on the rest of your architecture. And if for any reason the cache is to break, then all of your dependencies just get flooded with a whole bunch of traffic all of a sudden. And that can really knock out huge chunks of your ecosystem if it's not prepared carefully. We had a cache break and we had no idea where it was coming from. There was no way of finding out. There was no open tracing. There was no service mesh tracking anything. There was no proxies between anything. It was just purely random Heroku instances calling random Heroku instances. But the one clue that we had was user agent Faraday 091. And that's a common HTTP client. All of our apps were using it. But luckily, we were able to search for Gem Faraday just across the entire organization in GitHub, which is not how you should do this stuff, but it's all we could think of doing. And all of the apps, thankfully, were so behind on keeping up with their dependencies that it made it a unique fingerprint that we could look for. And so we looked through each of the apps log files, and that one would be on 091, that one would be on 081, right? They all had different versions, different levels of old with different numbers of security bugs and problems in. And then eventually we found the right one. We found just this one app that was on 091. And so we took down the server and just went, screw that app. That one can go down. And that solved the problem. I mean, that app was gone, but the rest of the architecture was okay because this little server was no longer obliterating the monolith that everything else required to run. There's a lot of solutions to this. The most basic thing in the world is to put user agent with your app name. And if you can, put like the version number or like the commit hash of the version that's being deployed, just so you know what's going on. And if something weird is happening, be like, oh, there's like an errant old instance running, but that's edge casey. At least put the app name. And then setting up something like open telemetry. Open tracing is what it used to be called. They merged it with some other stuff. And that will show you like A through B through C. It will show you the request as it passes through all these different services and different responses come back, and it can track a single transaction, which is really helpful. Advanced move is you can use a service mesh to specifically set which apps are allowed to talk to what. Problem that we have quite often is that you start off with just A and B talking to it, and that's what your documentation says. That's what your notes and your architectural diagrams say. But some other service has quickly started calling it because they had to get something, and they might be the ones causing the problem, and no one knows that they're doing that. So if you set up a service mesh, you can say these are allowed to talk to it, and if you would like to talk to it, you have to like ask the ops team to enable that. And service meshes usually have some sort of tracing ready to go. So really, I think if you are using the microservice architecture without using a service mesh, you're probably just going to have a distributed monolith. There's a lot of different things this term means, a lot of different problems with distributed monoliths, but basically if you just have a bunch of random stuff calling a bunch of random stuff, you have no control over it, and you have no limitations on those network interactions in any way, no timeouts, no circuit breakers, then you don't really have a microservice architecture. It really is something scary. The chap called Scott something had a brilliant quote. He said, if you switch one of the microservices off and anything else breaks, you don't really have a microservice architecture, you have a distributed monolith. And things can start off really well planned. They can start off really simple, and you've got a few different UIs and a few different APIs, and maybe occasionally things will call another API, but over time, more interfaces need more functionality from more of your other services. You want more integration, more everything. And everything just starts calling everything. And it's just a mess, and there's no clear separation of concerns, and everything's like syncing with everything else, and everything's copying data everywhere. And if you deploy a change to one thing, everything else breaks. If one gets slow, everything else crashes. And that was exactly how it was at Unnamed Coworking Company. We had these two giant monoliths in the middle that required each other, and that everything else required, and they required a lot of other things. So there was no real separation between upstream and downstream dependencies. Everything just was a octopus getting all entangled with everything else. And there are a lot of problems there. Loads and loads of apps, 50 to 100 APIs with different apps. And they were all quite badly written, and they were just randomly on Heroku pointing at each other. And so you'd get these random transactions that would sometimes take 30 seconds. And the only reason they stopped at 30 is because Heroku would chop them off. They would have probably gone on for much longer. And that led to these awful New Relic graphs that you'd see where performance would just spike. And this is just the averages as well. This isn't even like the 95th percentile. So this isn't like things were actually taking a second and a half. They were taking much longer. But this dark green spike at the top is web external. That means that this service has been waiting for some other API for like a second and a half. And you can see that that's also caused a bump in request queuing, because there's only a certain number of web workers available, and they're spending all of their time waiting for this other API to do something, which means they can't do anything because they're just stuck. So that means that Heroku starts to stack up these requests of other people trying to talk to your API, so that hopefully it can serve them later before they time out. And this would happen all the time. Really bad knock-on effects. So at first, I kind of struggled to understand what that really meant. Like I struggled to visualize like why would setting timeouts or how would that help? If stuff's slow, it's going to be slow. But the problem is if you have service A, which has a bunch of different endpoints, and one of them, endpoint OK, we'll call it, just calls the database and returns some information. That one's quite easy. That's probably not going to have too much trouble. But this other endpoint that we'll just call slow needs to talk to service B. And service B right now is incredibly slow, maybe because it's waiting for C and D and E, but whatever, B is slow right now. And what that means is if you have only six, we'll just say six worker processes, sometimes they're called threads or dynos, or there's a lot of different ways of breaking this down, but you have six different things responding to web traffic, right? And of those six, one of the requests was for the slow endpoint. So great, that means 5 out of 6, they respond in 50 milliseconds or whatever, you're good. More requests can now be handled, right? And a few more people have requested slow. That request number 3 is still waiting for that slow response to come to be resolved. And now we've got request 8 and request 11 are stuck on that slow endpoint. Meanwhile, 7, 9, and 10 quickly responding and asking for more, more traffic is coming into those because they're available now. And damn it, 3 more people have wanted the slow endpoint. Now, all of our worker threads are completely stuck. All of our web threads are completely stuck on trying to solve this slow thing. And because no one in the company has set any timeouts anywhere on anything, it's going to sit there for as long as it can until Heroku tells it to stop. So yeah, this would happen a lot. And request queuing was a real problem. It would just kind of back up and up and up, and people would spend forever waiting for a request to start. And so the problem here is that any random API could take out everything depending on what the arrows were doing. Every now and then, something like the members network API, it was like Facebook, but specifically for this co-working company, for some reason, they would deploy some change, like they would run a migration that locked a table and that caused performance issues, or they would make an update to a query that was missing an index, and that would make a query really slow when it used to be really fast. Whatever was going on, anything that made that API go slow would trigger this cascading failure, right? Because there's no timeouts anywhere. So its stability just spreads like a fire. And that would crash the Rooms API for like booking meeting rooms. And that would crash the user company API, which is one of these 2 giant mega monoliths. And because that one crashed, well, now everything that talks to either of those 2 is crashed and slow and waiting for everything else. And we've even spread it to the other monolith because these 2 mega monoliths both require each other, right? Which means that now everything's on fire and those 2 mega monoliths just thrash and make each other worse. So yeah, the problem there is that people would just stand around and be like, this happens, it happens all the time. Distributed systems are hard. Sure, but there are solutions to these problems. Basically, they would treat the problem here was that like, oh, well, there was an issue with the members network API. The problem in our post-mortem was that we deployed a bad migration, so we should change how we do migrations, or we made a mistake with indexes, so we'll be more careful to make sure that we check indexes. And they would treat the symptom every time and not the overarching architectural issues that meant that if there was a problem with any one API, that everything else would crash. A lot of the time what they do is they just spin up more servers and more instances trying to like fend off the trouble. And that doesn't really help. It just like buys you a few more minutes before all your threads are stuck. And it also like there's actually a climate crisis going on and burning resources and literally burning the world to the ground just because we can't design good architectural structures is not the solution. The internet already accounts for 3.7% of global emissions. And so just like throwing servers at poor design is not the way to go. General recommendation, if you can't make a good monolith with good separation of concerns in the same code base, don't start adding network calls. I'm not the first person to say this, but like I really can't emphasize that enough. Microservices aren't necessarily better every time. And you really do need a high level of understanding of network interactions to be able to make them work well, especially using things like service mesh. But one thing you can do is you can create service level agreements for your APIs and stick to them. You can say this API will always respond in 1 second, always. And if anything else goes wrong, we'll jump at that like it's down. We'll panic and make sure it always is less than 1 second, or even less if you can. And then when you're calling an API, set a timeout on every single call. Always set a timeout, and it should match the SLA if there is one, right? And then basically expect everything to fail and be pleasantly surprised when it doesn't. Never expect a request to work. It probably won't. When something goes wrong, you can queue requests up for later. You can back off and try. So you're not just going, is it good yet? Is it good yet? Is it good yet? Is it good yet? Because now you're thrashing that server. Or you can also hide a feature. I've seen people just hide map view when the map server's broken. You get rid of the autocomplete functionality when the autocomplete search is broken. You can just kind of like make things react based on what's working and what's not right now. And setting timeouts is easy. Most HTTP clients will have a timeout option. This would be 5 seconds. So if I haven't got the whole response done in my status code in 5 seconds, I'm gone. And 5 seconds is still a long time. This code is in a background worker, not in the web thread. That's too long for a web thread. And then open timeout is in some HTTP clients is like, I need to know within 2 seconds, this server is going to start working on my thing. Otherwise, I'm out of here. So these numbers don't add. It's within 2 seconds, you better have started this job. And within 5 seconds, you better have finished this job, not 7 seconds. Craziest solution problem we had was busy days in Australia, nobody poops. Really weird real world problems happening from this. Let's look at this little bit of the architecture here. We've got a receptionist app, kind of like a front desk situation. And they'd use that to check people in and see who's where and let people know about meetings and things like that. And that would talk to a lot of different apps, but specifically here, the user and company API. That would, for some reason, talk to an API that was maintained by another company, which is called the keycard API, the wobbly bad keycard API. If you've ever been into like an office building and you have a keycard, you have to tap it against the door to get in. We had those, and the keycards would talk to some other service. That wasn't the problem. But we had like a gateway API that would say, Frank owns this card, and this card should let you into these buildings and these floors. And that gateway was the problem. Basically, on the first of the month, all of the new customers would turn up to access their new office that they've just paid a whole bunch of money for, right? They're excited, they want to get in and get started with their startup work. That's very important. And they wouldn't be able to get into the building because, basically, there were only 3 instances of this gateway API. There was one on the East Coast, one on the West Coast, and then other. And at the time, there wasn't really that much other going on. I think it was like an EC2 micro instance because there wasn't really that much traffic. But that company never noticed that traffic was increasing. And so as we got more and more buildings, other got busier and busier. And when it looked like this, it still wasn't that bad. But by the time the company had offices all over the world, it meant that other was pretty strained. And so just Australia and kind of East Asia, once that started to really build up traffic, it would just crash the entire company for the entire day pretty much. Because what would happen is the keycard API would get overloaded, and that would basically mean that the people on the front desk are sitting there trying to add that card. There's a queue of 10 people, right? And the first person is there like, right, Frank, let's give you this card, let's hook it up. And that goes through the ID, through the user and company API. And the wobbly bad keycard API is being wobbly and bad, slowing down, doesn't work, might take 30 seconds, might take 2 minutes to get your no, at which point front desk notices that, it didn't work, let's try again. Wait another 30 seconds, another 2 minutes, didn't work, try again, right? And that queue of people are now mad because they're paying loads of money, and this is the first day of their contract. Their first experience is they literally can't get into the building. So what they'd end up doing is just saying like, oh, go and we'll just let you in through the front door ourselves. And then if you need anything, let us know. And that would mean they couldn't go to the toilet without going to find an employee who could let them in, because the toilets, you need the key cards to get in there as well. And this would just be a really bad experience. But not only did that make the whole kind of keycard thing a problem, right? It would also crash this monolith that all these other services required. And because this monolith not only handled everything to do with like user information, company information, and keycard logic, but it was also handling OAuth tokens for everything. So that meant that just everything crashed. And so even though you got into your new office today, none of the systems would work. You couldn't book a conference room. You couldn't do anything. And it just looked like a shit show on the first of the month, every month. So I was trying to fix that. Like when I found out that was going on, I was like, let's not just let that happen every month, and started to work on solutions. We looked at, we implemented a traffic proxy. At the time we used RunScope. That's not around anymore as a proxy, but there's a bunch of other things around, and we just funnel all of our traffic through that. And they were saying nothing is slower than 100 milliseconds. And I'm saying, I have evidence that that's not true. And they tried to blame us, but I was able to share those requests with them, and they dug through everything, and they found out that their logging system, if it was more than a second, would just give up, because clearly that was a mistake. So 100% of their requests were good because they were ignoring the errors. I also pointed out, like, hey, I've got these 2-minute responses that are giving a 502, and their response was, oh man, nothing should ever give a 502, it should 200 on an error. And my eyes started to twitch a little bit, and I was like, I don't have time to get into that conversation, but can we focus on the 2-minute part, please? Oh yeah, that's weird too. So the first step was, because we had no trust in them actually solving the problems, I basically copied and pasted all of the code from the user and company API over to the keycard service and redirected all the traffic to that, rerouted the traffic. And it was still synchronous, it was still bad, but it meant that when the wobbly bad keycard API crashed, only the keycard service crashed, because I put timeouts on the request. Or no, sorry, because we redirected the receptionist app to the keycard service, and it didn't touch the monolith. So it meant that the sync service would crash, and that's okay for now. You still have the same problem with people being backed up, but you haven't taken down the entire company in the process. The next step was to make an asynchronous service so that requests could go back through to the user and company API, but it would basically just store the request for that keycard to be added for that person on that building in a background worker. And then if the wobbly bad keycard API was being slow, it would just retry and retry and retry. We put timers on it saying, if it's taking longer than 10 minutes, send them an email and let them know we'll work on it. And then we can send them an email when it's done. And that pretty much solved it. And then eventually they made their API not be bad. But that was just purely a case of how long will it take to get your keycard, and not the entire company is down. So demand an SLA for third-party services, pipe external traffic through proxies like Resurface or Istio. Really try and avoid putting your API requests in a web thread whenever possible. It's not always possible, but like usually it is. And it's especially important if they're not under your control, because you don't want to be completely reliant on something that you don't own. It might take months for them to fix it, or they might lie about it in the meantime. And you want to use background workers and event-driven APIs for things that can happen later. So even like sending an email via like send mail API, anything that requires going to another API, you can usually do that later. The last part of the distributed monolith is what I like to call mutually assured destruction. This part of the diagram, if you have noticed it, is the worst thing possible, because what would happen? Something as simple as getting information about a user was just this giant JSON request that had like 200 kilobytes of JSON for an average user. And sometimes on the collection, you'd get even more. We had to just remove the collection page because it had 200 kilobytes of JSON per user, 100 users. And that response could take 10 to 20 seconds, like really, really slow. And it was a mixture of stuff like basic user information, locale, phone number, kind of profile stuff, all of the locations that that user is in, and the companies that user belongs to, and then the locations that those companies have access to, were all jammed into this one thing by default. Not you can choose to include it if you want. It's jammed in there by default, which is terrible. What it generally meant was whenever the client was trying to find out some information about subscription and billing stuff, it would need to try and find the user's locale so it could give it the right currency, or I guess, or language, or whatever it was. It needed to find out what the locale was. So the client, so the subscription and billing API, one of these two mega monoliths, it would call the other mega monolith to say, hey, user 123, what's their locale? And because at some point they decided to start jamming this locations and company locations data into that response by default, it meant that the user and company API was now asking the other monolith that was originally doing the request to get this data that it doesn't care about but needs to do. And those might take 4 or 7 seconds to respond. So it meant that each monolith had not only a reliance on itself, but back to the original caller. And that might take 20 seconds if they're both working. Again, none of it's cached. So yeah, if the user and company API for any reason started to go slow, it would mean that the subscription and billing service is now slow. And that would mean that the ID is crashing because it's waiting for subscription. And then, of course, subscription crashes because it's trying to wait for ID. So I like to call that a double knockout, and it would happen all the time. And guess what? Timeouts help there as well. The real solution was basically we couldn't really change users 123. So what we did was we just made a new locale endpoint that just had the locale information, and then people can request that. And we put cache control on there to be like, they're not going to change their locale that often, mate. Every day is fine. So solutions there: stop designing APIs for HTTP1. You don't need to smash everything into one mega call like we're doing CSS combination. That's a thing that fell out of fashion for CSS and image sprites. They've all stopped doing it. For some reason in API world, we still do it. You can use HTTP 2 and 3 to multiplex multiple requests. It's a lot quicker a lot of the time. And it means that clients can only request more data if they want it, which is what requests are for. You just request what you want, and you can put caches on things to speed things up to make that time back. And using timeouts and circuit breakers means that simple requests can succeed even if complicated requests are currently failing, and you can do things differently if they are. And then you want to get an API architecture and governance team to review changes so things don't start off nice when you're whiteboarding and then grow into a mess over time. If you want to do that, I work for a company called Stoplight.io, which I've already mentioned. We make the whole API design first workflow easy. All of the open API lives in your GitHub repo, so you can like see pull requests changing it and go, oh, that's a bad idea, and a bunch of other cool stuff like that. So on that note, I'd like to thank you all for listening. Sorry I couldn't be there. I hope the sound was okay. And we've got a little bit of time left for questions, if you want to do that. Don't know what FD is. That's a typo. Come back over here.
Thank you very much, Phil.
Hey, thank you. Let me stop showing my screen a second, eh?
Thank you very much, Phil.
Hey.
You still there? Yeah, okay.
Yes.
Are there any questions in the assistance or maybe online? No questions?
Oh, not a dev question, but curious how long you were at the Unnamed company. It was about 1.5 years. That was about all I could handle of firefighting every single day.
Could you repeat, please? I didn't understand properly, sorry.
Yeah, someone was asking how long I was at Unnamed Coworking Company, and it was about 18 months. That was about all I could handle for firefighting every single day, putting out problems, P1s, P0s every day. Hard to do that for too long.
Oh, okay. Okay, I can see. Yeah.
Ooh, is Stoplight.io supporting JSON LD and APIs platform? Not currently. We focus on open API tooling, and you can use that to describe pretty much any type of HTTP-based API, but there's no formal support for JSON LD. It is something I'd like to look into. So if you want to talk to me on Twitter or wherever. Yeah, let's talk about it.
Okay, great. Let's do that. Thank you very much.
Yeah. Oh, and do I have a blog or something where you talk about what I just presented? Yeah. So APIsyouwon'thate.com. We can try and there's a link to a lot of it. If you have the slides, I put a link to the slides in the talk, in the chat here. And yes, there's a lot of links to kind of blog posts and stuff there.
Don't hesitate to share those links also on the live stream, so people online can also follow those links. I don't know if it's possible to share the links directly on live stream.
There we go. I put APIs you won't hate. Can't spell anything. You won't hate.com. Got it.
Okay. Thank you very much, Phil. In a few moments, we're going to welcome here in this room Samuel Rosé, who's going to talk about JSON-LD, and then Nicolas Grecas, who's going to talk about Symfony runtime. And first, we're going to make a short break. We're going to see you there, everybody, at 4:25. On va faire une petite pause. On se retrouve à 16h25 avec Samuel Rosé qui va nous parler de JSON-LD et Nicolas Grecas qui va nous parler de Symfony Runtime. À tout à l'heure.